Okay, welcome back. We're talking about 1.6, which is formulas. So, in math, there are oftentimes equations that we see so often that we just kind of make note of them and we call them formulas, right? Some of those formulas you might see are like the perimeter of a rectangle. A rectangle is two sets of parallel lines, like this. We can call one of them a width. Doesn't really matter which one's the width. Call the other one the length if we want. But because it's a rectangle, the other side over here is the same as the first width, and this bottom part is the same as the top length, right? The perimeter is, if you start at one corner and just walk around the whole edge of the shape, that's the perimeter, right? So if I start at one edge here and I just start walking, I've walked L, and then I walk W, and then I add on another L, and then I add on another W. And I'm back to where I started, and this we're going to call the perimeter. We can simplify this because there's an L and an L, so I can say that my perimeter is two L's, and there's two W's, so I'll simplify it, 2L plus 2W. And this is a formula for the perimeter of a rectangle. And if you remember this, you don't have to go through and figure it out every time, you just know it's two lengths plus two widths. This one's fairly easy, most people can recite this one just by thinking about it just for a moment, right? And so we'll use that to answer questions like, let's say a rectangle has length of 10 feet and width of 7 feet. And if we're asked to find the perimeter, we can use that formula. The perimeter is equal to 2L plus 2W, or 2W plus 2L, it doesn't matter, right? I know the length is 10 feet, so that is to say replace the L with a 10. And I know the width is 7 feet, so I'm going to replace the W with a 7, right? And I can then just pop this number out. 2 times 10 is 20, 2 sevens is 14, and if I add the two together, 34. So the perimeter of this rectangle is 34, and I have it, right? Okay. Good. We can also take a look at the area of a rectangle. That same rectangle, let's say we have that W, L. Area is defined as the width multiplied by the length, right? It's just those two things multiplied, right? So if I have the same rectangle up here and I want to find the area, again, all I have to do is replace W and L. The width was 7, the length was 10, and so I get 7 times 10, so this particular rectangle up here has an area of 70, right? When we're talking about perimeter, this would just be feet. When we're talking about area, this would be feet squared, because there's a foot unit in the width and a foot unit in the length, and to have the square indicates that it's a two-dimensional measure, right? And there we have it. We have two then formulas for rectangles, one for the perimeter and one for the area. let's look at let's go back to perimeter for a moment. Let's talk about a triangle. Let's say a triangle has sides A, B, and C. Then the perimeter, you can see this, if you start at one corner and walk around, you get A, and then you get B, and then you get C. So it's fairly easy. Any perimeter is just going to be the sum of all of the sides, right? If you have a nonagon, right, nonagon, you're going to have 9 different sides that you're going to add up. In this case, if I have values on here, if I have some triangle with actual numbers in here, I just have to replace these values. A is 12, B is 13, C is 14, right? So I get 39 out of this. So the perimeter one, not too hard, especially when it's a triangle is just the sum of all of the sides, right? Okay. Now we know that the area of a rectangle was the length times the width. But if we have some funky weird shapes, right? Let's say this is 10 down here, this is 13 up here. Let's say this is 5 and 5, and let's say this is 3, right? And we're not given all of the sides, but let's say they ask us to figure out what the area of this shape is, right? Well, it's easy to then cut it into rectangles. And there's more than one way to do it, but here's a way. Just draw yourself a dotted line right there, and you have rectangle 1, and you have rectangle 2, right? So the area of rectangle 1 is its width multiplied by its length, and I have both of those values. That's 13 times 10. So for rectangle 1, my area is 13 times 10, and that's 130. Right? That one was easy. Rectangle 2, though, I have 3, and I don't know the other measure. But I can figure it out, because if this is 13, that makes this 13, minus 5 more, that makes this guy 3, right? And therefore, for rectangle 2, I can argue then that the area is 3 times 3, that's just 9. And so the altogether area is just the two areas added together, so my total area is 139. And we can do that with all sorts of shapes, right? We can get all sorts of weird shapes, cut them into little rectangles, and figure out however many rectangles we have to add together to get my final area. Let's take a look at perhaps another one. I think there's a good example in the book below. Let me see. Not too bad. Let's take a look at this one. We're given kind of a backwards Utah. And we have, probably not going to be to scale, because I'm, trying to make it a little bit better. We're given that side is 6, this side is 8. The bottom is also 6. And then I have 4 for the top. That's what we're given, right? Now there's a number of ways that I can do this. I can cut it right down the middle right here. The book actually does that below, if you read down. You can also cut it this way. So I'm going to cut it this way and see if we get the same answer as if we cut it down the middle like the book does. Spoiler alert, we will. But let's do it. That means I have rectangle 1 here. Rectangle 1 is, one side of it is 6 and the other side is also 6. You don't want to use 8 because this distance here isn't 8, this bigger distance is, but that's not rectangle 1, that's rectangle 1 plus some stuff. So for rectangle 1, I have 6 times 6 is 36. And for rectangle 2, I have 4 multiplied by however big this little bit is. Which I can tell is 2 because this is 8. And if I lose this part of it, 8 minus that 6 is 2. So rectangle 2 is 4 times 2, which is 8. Add those two together, and I get 44. And that is what the book got by cutting it down the middle instead, right? Okay. All right. There are other formulas. One that we'll use quite often is the distance, rate, and time. And that formula is the distance that something travels is equal to the rate multiplied by the time, right? How fast it's moving multiplied by how long it's moving, right? So we'll see this pop up quite a bit. You'll see it in later chapters where they're like, hey, here's the distance, rate, time. They're going to expect you to be able to recall this formula, right? So something simple like, say, a horse runs for 30, let's say 3 hours at a rate, let's just say at, the implication is that there's a rate here, 40 miles per hour. I don't know how fast horses run, but I imagine one might make it to 40 miles an hour. Probably not for 3 hours, but hey, this is math class, not reality yet, so work with me. But if we want to find out how far this horse goes, the distance is equal to rate times time. The rate is 40 miles per hour. The time is in hours, so 3, this means that this horse is running 120 miles. Is that reality? I don't know. I don't clock horses very often. But for this problem, there we are. Math class is where we end up with 25 watermelons and nobody asks what we're doing with them, so let's just roll with these numbers, shall we? All right. Now a big one, more general equations deal with variations, right? So I'm going to stop this video here and I'm going to create a new one to talk about variations. Look for that below and see you in a sec.